So last lecture, before the break, we were talking about eigenvalues and eigenvectors and how everything pretty much boiled down to that lecture in terms of the central piece of linear algebra, at least when you learn it for the first time or for the first introduction course into linear algebra. That's usually the way um, we piece everything together, is this idea of eigenvalues and eigenvectors. Um, so let's just quickly recall. Recall that an eigenvalue lambda um, and an eigenvector is associated with a matrix A, given in such a way that when you multiply the eigenvector with the matrix, it's really like multiplying a scalar by that eigenvalue. So that was the central piece. That was the central equation of last lecture. And as a result, we were finding ways we found a way to discover or to compute the eigenvalues and the eigenvectors. So to find the eigenvalues of A, need to solve the characteristic polynomial. And the characteristic polynomial is given by the determinant of A minus lambda I equals 0. So that's the polynomial. When you compute the determinant of this expression, you get a polynomial in terms of lambda. And when you solve that characteristic polynomial, the roots are the eigenvalues. And again, where did this expression come from? Why determinant, and why A minus lambda I, and why 0? And this boils down or comes from the very nature of this problem, which if you were to solve for V, another thing, the eigenvector is non-zero. That was another important thing. It's a non-zero eigenvector. So when you solve for V, this is the equation that you get. You get a homogeneous system. And if you have a homogeneous system, with non-trivial solutions homogeneous system with non-trivial solutions implies what? Implies that implies that the matrix A minus lambda I is non-invertible. If you're not invertible, that means that the determinant of that matrix is 0. And it means several other things, right? So that's the reason why we set the determinant of this matrix here equal to 0, is because in solving for V, right? In solving for V, which is non-trivial, which is non-zero, which when you say non-trivial, you mean it's not 0. So it's a non-trivial solution to this homogeneous system. That means that this matrix must be non-invertible, meaning that it must be singular, which means that the determinant of this matrix must equal 0. And so that's why when we perform this procedure of finding the determinant of this matrix and you have this unknown, this becomes a polynomial. It converts itself to a polynomial. And so associated with those eigenvalues, which are the roots of the characteristic polynomial, to find the eigenvectors, of A, need to solve the system A minus lambda I V. So solve the system for the specified eigenvalue. So whenever we have a specified eigenvalue, to find the eigenvector associated with it, I replace the lambda with the specific number, and then I find what is the null space, essentially. So, or equivalently, find the basis of the null space of A minus lambda I. Okay. And the null space of the A minus lambda I matrix, the null space is also known as the eigenspace. And the basis of that eigenspace is known as the eigenbasis, is an eigenbasis. So this word eigen is going to be peppered in throughout most of our terminology. Okay, so we got eigenbases now from eigenspaces, and the eigenspaces come from the eigenvalues, which are used to find the eigenvectors. So there's a lot of eigen, and more eigen. Okay. So let's see this. So, okay. So let's look at an example. We got 6, 0, 1, 3, negative 2, 0. -8, 0, -3. Right? And I want to find the following. Find the following. The first, I want to find the characteristic polynomial P lambda. Second thing is find the eigenvalues of A. And then the third thing is to find the eigenvectors of A. Yes, sorry. Okay, so is everybody okay with where we are? So I first want to find the characteristic polynomial. So what's the characteristic polynomial again? The determinant of A minus lambda I, and the determinant will be what? 6 minus lambda, 3 minus 8, 0, -2 minus lambda, 0, 1, 0, -3 minus lambda. Okay, so this is the first thing that we want to find. And this, of course, is set equal to 0 because the assumption is that this expression here is the null space is has non-trivial solutions, which indicates that the matrix itself is singular and not invertible. So the determinant of that matrix must be 0. Now, how do we find the determinant of this matrix? Use the middle row, right? So you perform cofactor expansion along second row. So when you do that, remember, this is going to look like what? This is going to look like A21, C21 plus A22, C22 plus A23, C23. But A22 equals 1 equals 0. A23 equals 0. So those go away, right? Those become 0. So really, all we care about is A22, which is what? -2 minus lambda. Now, what's C22? C22 is -1 to the 2 plus 2 times the minor 2. And the minor comes from striking out the second column and the second row and finding the determinant of the given 2 by 2 matrix here. So this is 6 minus lambda, -8, 1, and you get -3 minus lambda. And then we have a 2 by 2 matrix. a 2 by 2 matrix that I can find the determinant of. This becomes 6 minus lambda. This is -3 minus lambda minus -8 times 1, which is +8. Again, this equals 0 the whole time. And this is -2 minus lambda. This is -18 minus 6 lambda plus 3 lambda plus lambda squared plus 8 equals 0. So this is lambda squared minus 3 lambda minus 10. -2 minus lambda equals 0. P lambda. And what do you notice? I can further factor, right? I can factor this further to what? What is lambda squared minus 3 lambda minus 10 factor into? Right, this is lambda minus 5, lambda plus 2. That equals 0. And P lambda. And this is the characteristic polynomial, but it's factored, of course. If you want to figure out like the standard form of the polynomial, you can also expand everything out. But this is the factored form of characteristic polynomial, or char poly of A. And then once we have it in factored form, what's good about it is I can find the solutions, right? So what's the solutions or the roots of characteristic polynomial? So lambda is equal to what? Again, the roots are the eigenvalues. We got -2 and 5. Oh, so actually we can write this a little neater, right? You can factor out the negative. You get lambda plus 2 squared times lambda minus 5. That equals 0. So that's the more compact form of the characteristic polynomial. And what we notice is that -2 is repeated. It's a repeated root. Okay. Okay. Does the repeated root mean anything? Well, actually, we'll start to see today that there is a significance to the repeatedness of the root. At the moment, it's just repeated, right? It's just a root that's repeated. But what you will see, though, is in the next step, we have to find the eigenvectors associated with the eigenvalue. Now, just to give you a little sneak peek, when you plug in that eigenvalue -2 into the A minus lambda I expression, you get a non-invertible matrix. Now, what we don't always know immediately is when I find the null space of that matrix, whether or not I get what's called enough, quote unquote, eigenvectors from it. That's all I'm going to say for now. But hopefully, as we continue on that particular line of thought, you'll see the significance of the repeatedness of the root. So right now it's just a repeated root. But it has something to do with the dimension of the eigenspace. It has something to do with that. Okay, so for example, I want to find now the eigenvectors. And of course, I get eigenvectors based upon the eigenvalues. So if I plug in -2 into I minus lambda I, what do I get? I get A plus 2I. So what was A? A was 6. So this is 6, 6, 3, -8, 0, -2, 0, 1, 0, -3, right? I'm adding that by 2, 2, 2. So when I add this, I get 8, I get 3, I get -8, I get 0, 0, 0, and I get 1, 0, -1. Right? I have one row of zeros. I can eliminate. I can put the 0 row on the bottom, the third row. I can switch that. And I'm also going to put the 1, 0, -1 on the first row. Because that way I can eliminate that 8 very easily by just multiplying the top row by -8 and then adding it to the second row. So again, I find the null space by finding the row reduced echelon form. So this is 1, 0, -1. This is 0. This will still be 3. And then when I multiply by -8, I get +8 and I get 0. And so when I continue doing this, I get 1, 0, -1, 0, 1, 0, 0, 0, 0. What does this row reduced echelon form tell me? Again, these are associated with the columns, right? So it tells me that x1 equals x3, x2 equals 0, and x3 is free. Now, why does this matter? Because the solution is simply the scalar of 1, 0, 1. Right? Let me just make sure I did this all fine. So this is my eigen. This is my eigen value. Because this is an eigen basis for the eigenspace, which is the null space of A plus 2I. Okay? So does that make sense? So the eigens, so let me just make this clear. The eigenbasis for lambda equaling -2 is the set of all scalar multiples of 1, 0, 1. Now the eigenvector for lambda equaling -2 is the vector 1, 0, 1. Okay. Now, just notice something. This is a repeated root, right? And the repeated root was 2. And I got one eigenvector. Just keep that in mind. Okay. And now the next one would be what? Lambda equaling 5. So when lambda equals 5, I want to find the null space for a minus 5i. So then a minus 5i, what does that equal? Again, I get 6, 3, negative 8, 0, negative 2, 0, and 1, 0, negative 3. And I'm subtracting that with 5, 5, 5, 0, 0, 0, 0. The rest is zeros. So when I subtract, I get 1, 3, negative 8. I get 0, 3, 0. And I get 1, 0, 2. Okay. I can rearrange the the second row and the third row, swap them. I get 1, 3, negative 8, 1, 0, 2, 0, 3, 0. Eliminate row the 1 underneath the 1 in the first column.
Professor, I think we were supposed to subtract. It wasn't supposed to negative 2 minus 5.
Oh, yes. That's right. Sorry. So this should be negative 7, right? And this should be negative 8. Pardon me for that. Yeah. So then when I swap this, I get negative 7, negative 8, right? Yeah, I got, I was adding the 5 instead of subtracting the 5. Okay. And so then to get rid of that 1 here, I negate the first row with the second and then add to the second, and I get 1, 3, negative 8. I get 0, I get negative 3, and I get 0. And I get 0, negative 7, 0. And then what do you notice? You notice that this negative 3, I can make this a 1, clear this, and I clear that. So then what this is going to look like is 1, 0, negative 8, 0, 1, 0, and then 0, 0, 0. This is in row reduced echelon form. What information does this give me? It gives me that x1 equals 8, x3. It gives me that x2 again is 0, and x3 is also the free variable. So my eigenvector is t of 8, 0, 1. So what's the eigenbasis for lambda equaling negative positive 5? The basis is the set of all vectors such that t is a scalar multiple of 801. So any scalar multiple of 801 is an eigenbasis, or lambda equaling 5, and then the eigenvector for lambda equaling 5 is just the basis vector of the eigenbasis, which would be 801. Now, so far, we just are interested in finding the eigenbasis, the eigenvectors and the eigenvalues. That's the extent of what we've been considering so far. There's several things to notice, to observe, and to understand about eigenvectors. So one note is that eigenvectors of distinct eigenvalues are linearly independent. Okay. That's pretty important. When you create this, when you find the eigenvectors of a matrix, they're always going to be linearly independent from distinct eigenvalues. So if you compare the eigenvector A01 and compare it to the vector 101, then you have a linearly independent set because they're not scalar multiples of one another. Now, in this particular example, we only get two eigenvectors. But this is this is a 3 by 3 matrix. And the characteristic polynomial is a degree 3 polynomial. But yet we only get two eigenvectors. We get one from the repeated one, and we get one from the non-repeated one. I believe in the other examples that we did last class, we got the number of eigenvectors was the number of columns of your square matrix. The idea is that you can find a basis for the space that you're in, right? In this case, we would be in the R3 space. We can find a basis of R3 with finding the eigenvectors. If we were to have three eigenvectors, so if we have three eigenvectors in R3, then we have a basis automatically for R3. But in this case, we don't. We don't have one. Okay, just more general info on eigenvalues. On eigenvalues and vectors. So if A is an n by n matrix, the following statements are equivalent. The first one is that if lambda is an eigenvalue, this is just summarizing what we already know, okay? It's an eigenvalue of A. Then then lambda is a solution of the characteristic polynomial the determinant of A minus lambda I equals 0. 3, the system of equations A minus lambda I V equals 0 has a non-trivial solution. And yes, and the non-zero vector V is the eigenvector of A, where A times A times V is lambda V. Okay, so again, this is just a summary of what we already know, just bullet form. So all of these mean the same thing. Now let's relate eigenvalues with the invertibility of a matrix. So how are the eigenvalues of a matrix related to the determinant, related to whether or not, related to, sorry, the invertibility of the matrix A. So let's just go back to the example that we have. What was it again? It was 6, -3, -8. Sorry, +3. 0, -2, 0, and 1, 0, -3. Now, one way to test if this is invertible is to see if what the determinant is, right? So what's the determinant of A? How do we compute the determinant of this matrix? Just A, not A minus lambda I, just A. Cofactor, yeah. Yeah, so it's exactly the way we did the first time, right? We cofactor expansion along the second row. So what did that give us? That gave us -2, and then the 2 by 2 matrix, 6, -8, 1, -3. This becomes -2. This becomes -18 plus 8. This is -2 times -10. And then this gives us +20. And then what were the eigenvalues of A? Lambda is -2. Lambda is 5. But 2 was repeated twice. So if we multiply all the eigenvalues, what's the product? Product of the eigenvalues. Well, if I multiply all of them with the repeats, I get -2 squared times 5, which is what? 20 as well. So is that a coincidence? We just showed for this particular example, the determinant is really just a product of the eigenvalues. Should that be a surprise or should that be, yeah, that is another shortcut, right? So to find a determinant of a matrix, you'll need to actually compute the whole determinant if you could find the eigenvalues somehow nicely. And if you know the eigenvalues, you multiply them out and you get the determinant. But is that a surprise or is that something that we should have expected? So that's something maybe you could think about. How come? Why is it that the eigenvalues of a matrix are related to the determinant of the matrix? Now, how does that, how does this though, this little example that we did, how does this connect with the answer to the question that we have? How are the eigenvalues of a matrix related to invertibility of a matrix A? Can you guys tell me what would the eigenvalues tell me, or what would it, or what would the eigenvalues mean or represent, or what would this signal in terms of the matrix, and in terms of the invertibility of the matrix? Right. So then we can say, we can conclude, right? Conclusion. We can make a conclusion. Or you know what? Let's say call it a proposition. Proposition would be that if every eigenvalue of a matrix A is non-zero, then A is invertible. And this also goes the other way, right? If the matrix is invertible, then every eigenvalue must be, it must be non-zero. What's another way to say this? In the, I would say probably in the converse, or I should say, not the converse, but the, I want to say opposite, but I think the proper way would be contrapositive. What would be the contrapositive to this statement? No, the contrapositive of this statement. Do you guys remember that? Do you guys know that? So like if you have if P then Q, the contrapositive of the statement would be what? If not Q, then not P. Contrapositive is equivalent to the original if then statement. It's equivalent in terms of the truth value to it. So if P then Q is equivalent to saying if not Q, then not P. So our Q and P here, our P here would be every eigenvalue of the matrix A is non-zero, and our Q would be A is invertible. So if we find a contrapositive, so a lot of these theorems are built this way. They're expressed using logical statements. So if A is not invertible, then what? Then at least one eigenvalue is zero. So if my eigenvalue were 0, or at least one of them, it would be a non-invertible matrix. Sorry, I spelled non-invertible wrong. Okay. And because this is a this is not just a conditional statement. These are called conditional, right? If P then Q. This is also a biconditional. So if this is true, then this is true, then the other saying it in the converse would also be true. If A is invertible, then this is every eigenvalue must be non-zero. Similarly, if A is non-invertible, then at least one eigenvalue is 0, then the converse of this statement is also true. If if A has one, if A has at least a one one eigenvalue that's 0, then A is non-invertible. Okay. Now, how do we prove that to be true? We didn't prove it. We have the inclination to say, right? What's the inclination? The inclination that we have is that the determinant of a matrix is the product of the eigenvalues. This is not enough to make that claim true. It could have been a fluke. It could have been just a coincidence that this determinant, when I found it, was equal to the product. It could have been, but indeed it isn't. So we have to be more precise in proving it, such a statement as this. So the way we do that is we assume, right? We assume that this particular, uh, um, we assume this particular part of the conditional statement to be true. We assume that A has an eigenvalue that is 0. So suppose A has an eigenvalue lambda equals 0, right? So if lambda equals 0, remember what were the equivalent statements? If lambda equals 0, then lambda equals 0 is an eigenvalue of A, and then lambda equals 0 is a solution to the characteristic polynomial. So what is the characteristic polynomial? Well, the characteristic polynomial is the determinant of A minus lambda I. And because this isn't, one thing I forgot to say is that A is an n by n matrix, right? It's a square matrix. We only talk about eigenvalues with square matrices. So we're going to have a characteristic polynomial, right? Where lambda is raised to the nth power plus, and then we have coefficients. I don't know, call it Cn1 lambda to the n minus 1 power plus all the way to C2 lambda squared plus C1 lambda plus C naught. This has to equal 0, right? So if I were to describe the characteristic polynomial, it would be an nth degree polynomial where you have lambda to the nth power being the leading term. This would be the characteristic polynomial in general, right? Abstractly, just in generalized. Now, if that's true, then what's also true? Then P of 0, right, would give me what? C to the 0, but this would have to be 0. Correct? Let me just see. But then what is C of 0 again? What is P of 0? Isn't this the determinant of A minus 0? And isn't this the determinant of A? Do you guys see the implication now? So this would mean that what? A is what? Not invertible. So did you see how we proved this statement above here? If A has an eigenvalue of being 0, then it's a solution of the characteristic polynomial, which would indicate that C0, right, is 0. And this whole thing equals 0. But this implies that the determinant of A minus 0, because that's what the eigenvalue is, would be 0, which would imply that the determinant of A is 0, which would imply that A is not invertible. So I was led from my assumption that the eigenvalue is 0, I was led to the conclusion that A is not invertible. Does that make sense?
Where is it that we see that C naught equals the determinant of zero of A?
Say it again. Where do we see?
Oh, I got it. I found it. Sorry.
Yeah, all of this is like from here, right? So we plug in 0 here, we plug in 0 here, and the determinant of A is 0. So then by the same nature, right? If the determinant, so then if the determinant is non-zero, so do you see that? So if the determinant was non-zero, then this would imply that Cn is not 0. So do you see the other way around? If the determinant here was non-zero, this would have to force C0 not to be 0. If C0 is not 0, then this characteristic polynomial can never have lambda equaling 0 as a root. So that forces the contrapositive to the statement to be true. If A is invertible, then eigenvalues had to be non-zero. So that's the rationale behind it. Okay. So you can tag this proposition to your list of equivalent statements starting from A is invertible. What does it mean to A is invertible? It means that the inverse exists. If the inverse exists, then you have a slew of things you can say, right? You can talk about the rank being full rank or being n, talk about the nullity being 0. You can talk about the determinant being non-zero. You could talk about now the eigenvalues have to all be non-zero, and so on and so forth. So now we have an additional statement that's equivalent to all the other statements of it being invertible. Okay. Okay, so that's all fine and dandy. So eigenvalues are cool because there's a relationship between eigenvalues and determinant. The null spaces of the eigenvectors are solutions to are part of the null space of the A minus lambda I matrix, and they form a linearly independent set. The eigenvectors, when you find all of them, they form a linearly independent set. What would be nice is that if your matrix has a full set of eigenvectors, which would be a basis for the full space that you're in. So all of this stuff is starting to come back. Now we're going to flip the switch a bit and head into a new realm related to this concept of eigenvalues and eigenvectors. And that deals with what's called the diagonalizability. Diagonalizability. And this is under the umbrella of factorization. So remember, I mentioned that we're going to be talking about factoring, quote unquote, matrices now, not just factoring polynomials, but factoring matrices. So what is this idea? So the idea is that, so again, recall this little equation is amazing, right? It's amazing how this little equation here, seemingly so simple, has so much, like there's so much we can talk about. So suppose, okay, suppose we have a n by n matrix A. And suppose that this n by n matrix has n distinct vectors. No, sorry, has n distinct eigenvalues. So we have eigenvalues lambda 1, lambda 2, all the way to lambda n. Okay, so we have n distinct eigenvalues. And also the assumption is that they're non-zero. So if you have non-zero eigenvalues, right, then you have an invertible matrix. So we have an invertible matrix that has n distinct eigenvalues. And because they're n distinct eigenvalues, for each eigenvalue, you're going to have this, you're going to have an eigenvector. So because of that, it has n distinct eigenvalues and n eigenvectors. And the eigenvectors are v1, v2, all the way to vn. So guess what we're going to do? Well, what do we know from here? We know that A vi is equal to lambda vi for for I going from 1 to all the way to n. Yes, Mir.
Oh no, this is up from a while ago. I apologize.
Was your question answered, or do you still have it?
Yeah, it was still when we were dealing with the vector, with the matrix, and we subtracted it wrong.
Oh, okay. Now, what happens if I were to sum this together? What would this look like? AV1 plus AV2 plus all the way to AV3, right? Oh, all the way to AVN. Which is the same thing as saying lambda V1 plus lambda V2 all the way to lambda 1 V1, lambda 2 V2, lambda n Vn. Right? Now, how can I express this? So let me put that. Yeah, so this would be the summation, right, of lambda I vi as I goes from 1 through n. And let me just copy this here. And let me copy this here. Is there a way for me to write this as a product of matrices on the right side? So on the right side, we have, remember what we have, scalar, vector, scalar, vector, scalar, vector. Is there a way that I can represent this as a product of two matrices? Yes, so what would that look like? Constant matrix times vector matrix. So your constant matrix, what do you mean by constant? Lambda? So something like what? Lambda. How, so the vector matrix would be what? Are you talking about like this? V1. So V1 would be the column vector. V2 would be the column vector. And then Vn would be the column vector, like that. Is that the vector matrix? So these are all columns. And then what would be the constant matrix? What would that look like? One column? Oh, so, okay. So where would be the column? Would it be on this side? It wouldn't be, it would be, this is a n by 1. So you're talking about something like this? Like lambda 1, lambda 2, lambda n, like this? Yeah, that's one way. That's definitely one way. Okay, let's leave that for now. How about the left side? What would that look like on the left side? Actually, yeah, I can see the difficulty of this. So for now, don't add them. Don't add them. Just treat them as columns. Treat them as columns for now. So if you treat them as columns, do you see how the left side does equal the right side? Do you see how the left side here, if this is a column AV1, this is really just lambda V1, right? Because of what we said here, AVI equals lambda VI. Now, if you understand matrix multiplication, I don't know if you guys remember back in the day, we talked about this. This is another way to describe matrix multiplication. This is really like saying A multiplied by the matrix where the columns are V1, V2, all the way to Vn. This is the same thing. Okay, and then there's no summation here. It's just this. And then how would we treat this? So this is the little tricky part, right? We would have also V1, V2, Vn, but then we would have a diagonal matrix. And if you notice, you can multiply these two things, right? And you get back this original arrangement. Because diagonal matrices, the beauty behind diagonal matrices is that you can commute them. You can commute. You can't do that with other matrices. So with diagonal matrices, you can change the order of multiplication and gives you the same thing because of its because of the fact that it's diagonal. Does that make sense? So in reality, this here should look like diagonal matrix times the vectors v1 all the way to vn. Because of the commutability of multiplying by diagonal matrices, and you can verify that yourself, you can change it. Now, what I'm going to do is I'm going to call this P. I'm going to call this diagonal matrix D. I'm going to call this A. And I'm going to call this P. Now, it looks like we just have a random equation here. But this is where the diagonalizability comes from. Now, because P is the matrix whose columns are the eigenvectors, which are linearly independent, if you have a full set of independent columns, linearly independent columns, then you have an invertible matrix. That's what it means to be invertible. So P is invertible by nature. If it's invertible, what exists? It's inverse. If that's the case, then can't I multiply both sides by P inverse? And guess what I get? I get a description here that fits the diagonalizability of A. I can rewrite this in many ways, right? I can also write this as the diagonal is equal to P inverse AP. If I do it the other way, if I multiply it by inverse here, I get that the diagonal matrix is equal to P inverse AP. Do you guys see what I just did here? This is a factorization of A. So what's the assumption? The assumption is that A has to have what? It has to have n linearly independent eigenvectors. If you have n linearly independent eigenvectors, then you have a diagonalizable matrix. If you don't have n linearly independent eigenvectors, then you cannot factorize the matrix in this fashion. So the example that we had originally, right? We had a 3x3 matrix. So we expected to have 3 linearly independent. That's kind of the expectation, but we only got 2. So the moment we got 2 linearly independent vectors only, eigenvectors only, then that implicates or implies that the matrix is not diagonalizable. So we cannot diagonalize that matrix. So there's a requirement. So to diagonalize a matrix, sorry, an n by n matrix, there must be n by n linearly independent vectors. Not n by n, sorry. There must be n linearly independent vectors. And this is an important, a necessary condition for diagonalizability. Diagonal. Does that make sense? So the matrix that we had originally, so if we look back at the example, A was 6, 3, -8, 0, -2, 0, and 1, 0, -3. The eigenvalues were -2 and 5. The eigenvectors was what? 1, 0, 1 and 8, 0, 1. If I had that correct, or was it a negative? Yes, 1, 0, 1. So we only had 2 vectors, but we need 3 for diagonalizability. So this is very important because just because you have an invertible matrix does not mean diagonalizable. So invertibility is not a condition for diagonalizable matrices. So this is a note. So note, an invertible matrix is not necessarily diagonalizable. Okay. Again, because you're invertible does not mean you're diagonalizable. Okay. So let's try to diagonalize the matrix 0, 0, -2, 1, 2, 1, 1, 0, 3. So if I want to diagonalize this, then I want to find a way to express A as a product of matrices where one of the matrix is the the vector, the matrix with whose column vectors are the eigenvectors, whose diagonal matrix are the eigenvalues, and whose whose other matrix is just the inverse of the matrix with the eigenvectors. So how do we proceed? Well, the first thing is to find the eigenvectors. To find the eigenvectors, to find the eigenvalues. So find the eigenvalues first. So now we can pick up speed with this, right? Because now finding the eigenvalues shouldn't be the hard part, because we should already know what to expect. What do we get? We get negative lambda, 2 minus lambda, 3 minus lambda, 1, negative 2, 0, 1, 1, 0. And it looks like we've done something like this before, right? We can row column expansion on the second column. And this becomes 2 minus lambda, negative lambda, negative 2, 1, 3 minus lambda equals 0. This is 2 minus lambda. This becomes negative lambda, 3 minus lambda plus 2 equals 0. So I get negative 3 lambda plus lambda squared plus 2. 2 minus lambda equals 0. And I get lambda squared minus 3 lambda plus 2. 2 minus lambda equals 0. This becomes 2 minus lambda. This is lambda minus 2, lambda minus 1. If you factor out the negative here, you get negative lambda minus 2, lambda minus 2, lambda minus 1. I get that lambda minus 2 squared, lambda minus 1 equals 0, and I get two eigenvalues, 1 and 2, right? So once I find the eigenvalues, I need to find the eigenvectors. So lambda equals 1. I need to find what happens when A minus I. What is A minus I? What is A minus I? I get negative 1, 1, 2. And I get 1, negative 2, 0. I get 1, 1, right? I believe we've done this same one. And so what you realize is that this is the same as this row here. I can eliminate one of them. And then I can write this as 1, 0, 2, 1, 1, 1, 0, 0, 0. And then I can eliminate the 1 underneath, the 1 in the first column, and I'm left with 1, 0, 2. This is 1, and then negative 2. This is negative 1. Right? And then I can solve. I got x1 equaling negative 2, x3, x2 equaling x3, and then x3 being the free variable. So then my eigenvector is negative 2, 1, 1, right? So that's the eigenvector associated with lambda equaling 1. And they had to find lambda equaling 2. So when lambda equals 2, what do we get? we get -2, 0, 1. This is 1, 0. This is a 1, 1. This is 0, -2. What do you notice when I find a row reduced echelon form? I just get 1, 0, 1, 0, 0, 0, 0, 0, 0. I got one pivot variable with two free variables. This is good news because that shows me I got x1 equaling -x3. I got x2 equaling 0, and I get well, actually, no, x2 is unknown, is the free variable. X3 is also free. So I get the set of vectors. What's going to be the set of vectors? I get t -1, 0, 1 plus s, which is 0, 1, 0. So I get two eigenvectors. I get two eigenvectors for the price of one eigenvalue. So I get the set -1, 0, 1 and 0, 1, 0. So then how do I set this up? What is A going to look like? What is A going to look like? Well, let's just break this down the way we had it, right? So the idea is that if I have the P, what is P again? P is the matrix whose column vectors are eigenvectors. So P is going to have, let's put lambda 1 being first. So the eigenvalue here is -2, 1, 1. So -2, 1, 1. And then the next column will be -1, 0, 1. And then 0, 1, 0. So when I multiply this by, what's my diagonal matrix? My diagonal matrix are going to be the diagonal matrix whose entries are associated with the columns here. So the first column here is associated with lambda being 1, 0, 0. The second column here is associated with lambda being 2. This will be 0, 2, 0, and this will be 0, 0, 2. Right? So then if I multiply this out, what would I get? Wouldn't I get, I would get this row, right? So I would get, hold on. I'll get the first row. I'll get -2, 1, 1, because all of these will be zeros. And then here, I'll get the second row, -2, 0, 2. And then if I multiply this third row here, I would get just the last row doubled, right? So 0, 2, 0, right? That's what would happen. And then what would be A? A would be we started out with what? 0, 0, -2, 1, 2, 1, 1, 0, 3. So that's A. And then P is the same column vector here, -2, 1, 1, -1, 0, 1, 0, 1, 0. So can we verify that P times D, which is this here, is the same as A times P? Does everybody see that? If I do this here, I get -2. Then the second column here would be what? 1, 2, 1. Would this also give me 1 here and so on? Well, what better way to do that than using a calculator? So let's speed up the process here. So second matrix, I'm going to edit. Oops. So this is 0, 0, -2, 1, 2, 1, 1, 0, 3. And then the B for the P, that's going to be -2, -1, 0, 1, 0, 1, 1, 1, 0. And then I'm going to put the diagonal matrix as D, also going to be 3 by 3. Nope, let me do that again. Second matrix. So edit 3 by 3. It's going to be 1. So all these are zeros. This will be 2. And then the bottom will be 2. This would be 0. And this would also be 0. So when I multiply the matrix P, in this case it's B, multiplied by D, I get this matrix. And then when I multiply A by that same matrix B, I get the same matrix. So here I've confirmed that A times P is equal to P times D. Okay? So I confirmed that A times P equals P times D, but that's not really what I'm interested in. I'm interested in factoring it or diagonalizing it, right? So the idea is I can do two things. I can either write D as P inverse AP, or that A is equal to P times D times P inverse.
Professor, we can only see your screen.
Yeah, I'm gonna change my screen in a bit. What I want to do is, what we need to do is find the inverse of the matrix that has the column vectors being the eigenvectors. So I can quickly do that by my matrix here. And so my P inverse is -1, 0, -1, 1, 0, 2, 1, 1, 1. So I found everything that I needed. So I can diagonalize my matrix by multiplying A with the matrix P and its inverse. So D, which is 1, 0, 0, 0, 2, 0, 0, 0, 2, is equal to P inverse -1, 1, 1, 0, 0, 1, -1, 2, 1, multiplied by my matrix A, which is 0, 0, -2, 1, 2, 1, 1, 0, 3, multiplied by P, which is -2, 1, 1, -1, 0, 1, 0, 1, 0. Again, this is P inverse. This is A, and this is P. So this just shows you that I'm able to multiply A in such a way to get a diagonal matrix. Not every matrix is this possible with. And I can also represent A, which is 0, 0, -2. And you can think of this as factoring. I'm factoring A as a product, or this case is going to be switched a bit. This is going to be -2, 1, -1, 0, 1, 0, 1, 0, multiplied by a diagonal matrix 1, 0, 0, 0, 2, 0, 0, 0, 2. And then let me just move this a little bit here. And so this would be -1, 1, 1, 0, 0, 1, -1, 2, 1. This is P and this is P. This is the diagonal matrix, and this is P inverse. That equals A. Oh, wow. You're on the last 2 pages. That's how many pages do you have? Yeah, if I counted all of these, like I probably will have, let's see, it's roughly around 10 pages for me every time. So probably like 200 or something, 200 pages. It's a lot of stuff, right? So you may be saying, wow, great. We're able to determine whether a matrix can be diagonalized in this weird way, where we utilize the eigenvectors and put them in the matrix and find the inverse of that matrix because it's invertible. Where when I multiply the matrix on the left and on the right with these two matrices, you get a diagonal matrix, which happens to be the eigenvalues on the diagonal entries. And similarly, I can factorize a diagonalizable matrix as a product of three matrices where the middle matrix is the diagonal and so on. Okay. And I guess now the question is sometimes can be said, okay, I can do this. Now, so what? What's so useful behind this? Well, there's a lot of things. There's a lot of things that that these matrices have in common. So if A is equal to P times D times P inverse, then A is what's called similar to D. So A and D are similar because of this relationship. So if any matrix has this kind of relationship where it's a product of two matrices being multiplied together with one being the inverse of the other, then they're similar. If they're similar, we have certain results. The results of similar matrices is that they have the same many things. So they have the same. They have the same determinant. They have the same invertibility. So if one is invertible, the other one has to be invertible. And they have the same rank. They have the same nullity because they have the same rank. It follows. They have the same trace. That's interesting. They have the same characteristic polynomial. And if you have the same characteristic polynomial, you have the same eigenvalues, obviously. And if you have the same eigenvalues, you have the same eigenvectors. Well, you have the same eigen, what is it? Yeah, it's an eigenspace dimension. So all these things you have together. So whenever you have a matrix with its diagonal matrix where the entries are the eigenvalues, you have everything being the same in terms of the determinant, being invertible, obviously, and then the rank and so on and so forth. Now, one last thing before we're done is that beyond the maybe the nice aspect of having these things being the same, these characteristics of matrices being the same, there's something that we can utilize, we can exploit the fact that we have this kind of relationship. So for example, if so for example, let's stick with the same example we had. So A. So if A is the same matrix that we had, 0, 0, -2, 1, 2, 1, and 1, 0, 3, right? Let's say I want to find A to the 5th. What would this what does the symbol mean? A to the 5th power. What would that mean that I have to do to A? Anything raised to the 5th power, what does that number imply? I multiply it to itself 5 times, right? So I would have to multiply 3 by 3, this 3 by 3 matrix to itself, and the product will appear 5 times, right? That A. Instead of doing that though, don't I know that this also equals P inverse dP, right? Now, if you notice, what happens when I square this? Doesn't this mean that I do P inverse dP multiplied by P inverse dP? But what do you know about multiplication of matrices? Isn't it associative? So can't I write this as PD? P times P inverse times D times P? But P times P inverse is what? The identity? So isn't this P inverse times D squared times P? And multiplying diagonal matrices really just multiplying or multiplying the entries along the diagonals, which in this case would just mean squaring the diagonal matrix. So then this would be the same thing as saying what? The diagonal matrix was 1, 2, 2. So this would be 1, 4, 4, 0, 0. And then I got P inverse, and then I got P here. And what if I want to find A3, A cubed? I would still have P inverse, right? By the same, if you see the pattern here, this would be D cubed times P. And so on and so forth. So if I want to find A to the 5th power, this is equivalent to saying P inverse multiplied by D to the 5th power times P. D to the 5th power would be 1, 32, 32, 0, 0, 0, 0, 0, 0. And then I would put P inverse on the left side, P inverse on the right, P on the right. And I can compute A to the 5th in this fashion, which is a bit easier, is a tad bit easier. Not that it's much better. If you have a calculator, just use a calculator, just raise it to the 5th power. But this helps with computation. So diagonalizing, for matrices that are diagonalizable, it helps. It kind of like sometimes improves the way we compute things. So not only does it have benefit in understanding the matrix A by understanding the matrix D. If you know D, then you know A. You see that? If you know the diagonal matrix, then you know all of this stuff about A. They're the same. But not just that, you can also compute higher powers of matrices by knowing the factorization of it using the diagonal matrix of eigenvalue entries. So that's another benefit for diagonalizing. And maybe to just conclude this lecture, I'm going to try to answer Mir's question about what significance is there to that repeated root. And I think I may have mentioned it a bit when I talk about diagonalizable matrices, but I'll just say it again just to reiterate. The matrix that we had here, right, had an eigenvalue that repeated twice, yet what happens? We only got one eigenvector from it. And we only had 2 eigenvalues in general, and we only had 2 eigenvectors. But to be diagonalizable, you need 3. Now, what's the significance of that and the repeated root? Well, the repeated root was repeated twice. This is called the algebraic multiplicity. So I'm talking about that on Wednesday, more specifically. But this is called the algebraic multiplicity because algebraically, as you see it here, you have a multiplicity of 2. Associated with that is called the geometric multiplicity. The geometric multiplicity is another way of saying the dimension of the eigenbasis. So the dimension of the eigenbasis is just 1. This is the geometric multiplicity. This does not equal the algebraic multiplicity. When the geometric and the algebraic multiplicity don't coincide, then you have something that's not diagonalizable. So diagonalizability is dependent upon whether or not the algebraic multiplicity of every eigenvalue equals its geometric multiplicity. So I hope that answers that question as to why or what significance is there for the repeatedness of a root. So if it repeats 3 times algebraically, then in order for it to be diagonalizable, you need that geometric multiplicity to also be 3, but it could be less, as we have seen. Okay, does that make sense?